Hello everyone, I'm Jivika Kancharla and today I'll be explaining you guys the solving of first question in homework 10 of the course probability and stochastic processes. So before we look at the solving of the question, let's have a quick look at the question itself. So the first question states that from my lecture notes, pages 1 to 50, collect the definitions and simple properties, that is probability, masses or density, mean and autocorrelation function of examples of stochastic processes, that is Poisson processes, Poisson increments, Poisson impulses, semi-random telegraph signal, random walk, Wiener process. Explain your understandings about these processes. Example, the mean of Poisson process is lambda t, which is a linear function of t. We feel it is reasonable the longer time we wait. The expected number of buses is larger. So in this question, we'll be explaining all of this. That is, we'll be explaining the definitions of these simple properties. So let's have a look at the solution. So a Poisson process is defined by a few properties that are listed below. Let's have a look at these properties one by one. The number n of t1, t2 of the points ti in the interval t1, t2 of length t is equal to t2 minus t1 is a Poisson random variable with parameters lambda t. That is p of n of t1, t1, t2 is equal to k will be equal to e power minus lambda t into lambda t power k by k factorial. If the intervals t1, t2 are in the intervals t1 and t2 and t3 and t4 will be independent of one another. For t is equal to a given time moment, there will be no more than one Poisson point. Using the points ti, we form a stochastic processes as we can see. Therefore, the first order probability will be equal to e power minus lambda d into lambda t power k by k factorial. So for this function, the expected value, which is mean, will be equal to expected of x of t is equal to lambda t, and the autocorrelation r of t1, t2 is equal to lambda square t1, t2 plus lambda into min of t1, t2. The autocovariance c of t1, t2 will be equal to lambda into min of t1, t2. That is, we know that the mean of this will be equal to lambda t, which is a linear function of t. Therefore, in our common sense, the longer time we wait for an expected number of buses is larger. Therefore, the autocorrelation function contains a term that is minimum of t1, t2, which comes from the property of an independent increment. In 1.2, we're asked to speak about Poisson increment processes. Therefore, the Poisson increment process can be defined by y of t is equal to x of t plus e minus x of t by e, where x of t is a Poisson process. Therefore, the first order probability masses will be p of y of t equal to n by e, which is equal to e power minus lambda e by lambda e power n by n factorial. Therefore, the mean of this function will be lambda t, and the autocorrelation will be lambda square for mod of t1 minus t2 is greater than epsilon, and lambda square plus lambda by e minus lambda into t1 minus t2 by epsilon square for t1 minus t2 is less than epsilon. The autocovariance will be 0, where t1 minus t2 is greater than e, and it will be equal to lambda by epsilon minus lambda into t1 minus t2 by epsilon square for t1 minus t2 is less than e. Now for point impulse process, the process z of t minus lambda has zero mean and autocorrelation. That is, z of t minus lambda is a white noise. Therefore, here we can see few examples of short noise in a real world. Therefore, we can define its output as linear time interval system. That is, it will have impulse response time, that is h of t, and its input as a Poisson impulse process. Therefore, the point impulse process will be defined as z of t is equal to dx of t by dt, where x of t is a Poisson process. Therefore, the mean will be lambda of t. The probability masses will have no definition, and the autocorrelation will be lambda square plus lambda into delta by t1 minus t2, and the autocovariance will be lambda delta into t1 minus t2. Now in 1.4, we should speak about the semi-random telegraph signal. Therefore, x of t will be defined based on Poisson points. The number n of t1, t2 of the points ti in the interval of t1, t2 of length t minus t2 minus t1 is a Poisson random variable with lambda t. Therefore, p of n of t1, t2 is equal to k. We know this is the definition, that is e power minus lambda t into lambda t power k by k factorial. Now this can be defined as x of t is equal to 1 if k is even and x of t is equal to -1 if k is odd. Therefore, for the first order probability masses, that is x of t, probability of x of t is equal to 1 will be equal to e power minus lambda t into e power lambda t plus e power minus lambda t by 2. If it is an odd function, that is k is x of t is equal to -1, then the probability will be e power minus lambda t into e power lambda t minus e power minus lambda t by 2. In this condition, the mean will be equal to e power minus 2 into lambda t. The autocorrelation will be e power minus 2 into lambda mod t1 minus t2. And the autocovariance will be equal to e power minus 2 lambda into t1 minus t2 minus e power minus 2 lambda into t1 minus t2. We know that probability is not equal to 1 by 2 because it starts with a positive sign. That is, p of x of t is equal to 1 should be higher than 1 by 2. That is this entire value, that p of x of t is equal to 1. We know that this value, it should be a little higher than 1. That is, when t tends to infinity, the probability of x of t equals to 1 will tend to 1, which matches with our expectations. Therefore, e of x of t is equal to e power minus 2 lambda tends to 0 when t tends to infinity, which matches our expectations. Therefore, t1, t2 are far away from x of t1 and x of t2 are less correlated. Now in 1.5, we should speak about the random telegraph signals. That is given y of t. We know that y of t is equal to a into x of t. That is, probability of a is equal to 1. Probability of a is equal to minus 1 will be equal to 1 by 2. Here x of t is a semi-random telegraph signal. Therefore, first order probability masses will be p of yt is equal to 1. P of yt is equal to -1 is equal to 1 by 2. In this condition, the mean is 0. The autocorrelation will be equal to e power minus 2 lambda mod t1 minus t2. The autocovariance will be e power minus 2 lambda into mod t1 minus t2. Therefore, the probability p of yt equals to 1, p of y of t equals to -1 is equal to 1 by 2. In this sense, y of t will be strict sense stationary and expected value will be constant, which also means that it is a strict sense stationary. Now, random walk. A random walk, that is, if you toss a fair coin n times, there is a probability that there are k number of heads and n tosses. Therefore, x of n of t is equal to ks minus n into k of s, that is 2k minus n of s. In this condition, the first order probability will be probability of x of t is equal to x into n of t, which is equal to rs, that is equal to n or n plus r by 2 into 1 by 2 power n for n of t greater than nt greater than t less than n plus 1 of t. The mean in this condition will be 0. The autocorrelation will be equal to min of n into s square. The autocovariance will also be same, that is min of n into s square. Now, from the probability masses, we know that n of t, there will be Gaussian density. The autocorrelation contains a term min t1, t2, which comes from an independent increments. And the Brownian motion, which is a Wiener process, we know w of t is equal to limit t tends to 0, s square by t tends to infinity, n tends to infinity, x of t, where x of t is a random walk. The first order density function f of w, t is equal to 1 by root 2 pi into alpha t into e power minus w square by 2 into alpha t. The mean is e of wt is equal to 0. The autocorrelation is equal to min of t1, t2 into alpha. The autocovariance is min of t1, t2 into alpha. A Minor process has a few characters. Let's have a quick look at them. The w naught is equal to 0. W has independent elements, it has Gaussian increments, and it also contains paths. That is, in a logarithmic way, if it is iterated, we can write it as limit t tends to infinity, super of w of t by mod by root 2 into t log t is equal to 1, almost definitely. Therefore, this is the solving of first question in homework 10.